Hey everyone, I thought I'd throw together a quick little video answer key for the 2020 sample question that was released this week for AP Calculus AB. So this is the first part of it, parts A and B, where you're given a table, T versus V, and you see at different times different velocities listed. This is the velocity of a particle, p, moving along the x-axis. It's given by a differentiable function, v sub p of t, where v sub p of t is measured in meters per hour and t is measured in hours. You can see selected values shown in the table, and particle p is at the origin at time t equals 0. Okay, in part A, it asks you to justify why there must be at least one time t in the interval from 0.3 to 2.8, at which v prime sub p of t, oh my gosh, it's so ridiculous to say. Okay, or let's just call that the acceleration of the particle equals 0 miles per hour per hour. Okay, why must the acceleration be equal to 0 somewhere in this interval is basically what that's saying. And here's what I want you to know. I feel like this is really important. You are most likely going to be asked to justify or to show why some value exists, okay? And what you are going to use to do that is one of the big value theorems, okay? There are 3 big value theorems that we look at in AP Calculus. The first one is intermediate value theorem. That's justifying the existence of a function value. Then there is the extreme value theorem. That's justifying the existence of an extreme value, like a max or a min. And finally, there is the mean value theorem, and that's justifying the existence of a derivative value, okay, of a rate value. And so that last one, the mean value theorem, is what we're going to use here. So be aware of them, have them readily available to look at, to see what you need to use to answer, a part of a question like this. So on this slide, I just put the mean value theorem just to remind you of its hypotheses and what we need to set up here. Okay, so we need a continuous function on a closed interval, differentiable on the open interval, and if we have that, then it says that there exists a point C in that open interval such that the derivative value at C is the same as the slope of the secant line through the endpoints. All right, what that really means for you is, first of all, you need to make sure to establish the fact that the mean value theorem would apply here. And it will apply because of this word. Since our velocity function is given to be a differentiable function, that means that it is both continuous and differentiable on this interval. So, you should write some sort of statement that would say that definitely MVT applies here because it is a differentiable function. First make sure that you establish that the hypotheses are satisfied. Okay. Once you've established that, then you can, move into the conclusion, and what you're going to work on is this right here. You're going to work on establishing the slope of the secant line, and notice that in this case we want to show that it would equal 0. Okay, sometimes they're a little bit trickier, meaning you need to find an interval that works. This time it's not. They give you exactly the interval that you need to be looking at. So go up to the table and take a look at when t is 0.3, v is 55. When t is 2.8, v is 55. And so if we do a slope between these two ordered pairs, okay, that's your f of b minus f of a over b minus a. I always like to say to my students, y2 minus y1 over x2 minus x1, because they're used to hearing, that formula from algebra class. In this case, that would be 55 minus 55 over 2.8 whoops, I'm jumping ahead of myself here. 2.8 minus 0.3, okay, which is 0. And so since we have the slope between these endpoints equal to 0, then we can see that by the mean value theorem, the derivative of v, or a, must equal 0 somewhere in that interval as well. Okay. You could also use here, by the way, Rolle's theorem. Rolle's theorem is just a special case of the mean value theorem, in my opinion. I don't know. I made that up, I think, but it seems like the same thing. All right, so, you know, you could look into Rolle's theorem as well. All right, so that's part A. Part B asks us to use a trapezoidal sum with 3 subintervals, and the really nice thing here, I don't know if, you know, if you're given one like this on the actual AP exam this year, would they set it up this nicely for you? I don't know that or not, but you have your subintervals even established for you so that you know exactly what you need to do here. You're looking at the interval from 0 to 0.3, 0.3 to 1.7, and 1.7 to 2.8. Just, you know, finding the area of each trapezoid on those subintervals and then getting the sum of the areas to do a trapezoidal sum. And that will approximate the integral from 0 to 2.8 of v sub p of t dt. All right, so here's how I like to do trapezoidal sums or any sort of approximation technique. I like to set up a table that looks like this. Okay, and the first thing that we're going to do is just put our subintervals in here. The first one is 0 to 0.3. The second one is 0.3 to 1.7. And the third one is 1.7 to 2.8. Oops, 1.7 to 2.8. Someday I will get like a pen that I can actually write. I'm just not there yet, like in one of those pads. Okay, don't send me one. That'd be great. All right, now the length of the subinterval, that gives you the height of each trapezoid. So the first one's nice and easy. The length of the subinterval is 0.3. That's the height of the trapezoid. The next one, 1.7 minus 0.3 gives us a width of the subinterval of 1.4, which again is also the height of the trapezoid. And finally, 2.8 minus 1.7, what's that, 1.1? That's the height of the third trapezoid. Now for your bases, by the way, I probably should have put this, the area of a trapezoid formula, area of a trap money Jenny. It's Trap Money Benny, by the way. It's not Trap Money Jenny. Sam, you know who you are. Okay. Here's our area of a trapezoid formula. Okay, so that's why I have these columns set up. All right, now for the bases. For each base, all you need to do is look at the function value at each endpoint of your subinterval. So I'm going to go up here and look at when time is 0, my velocity is 0. That's my base 1. When time is 0.3, my velocity is 55. That's base 2. I'm just going to keep going down this row. I know this one's 55 because it is the 0.3 value again. When time is 1.7, we have a negative 29. I didn't even notice that there was that negative in there. Makes sense, but all right. And finally, negative 29 here before I mess everything up, and 55 here again. I should have remembered that. All right, now, I didn't do this calculation ahead of time because I just like sort of sat down and started recording. So I'm going to do this with you. I'm going to do each area calculation and then we'll just add them up. That's how I like to do it. I just like to take it one step at a time. There's, you know, those trapezoidal formulas out there to make the work a little bit simpler. I mean, I don't really need to be typing in 0 plus 55 here, right? But I did. However, you need to be careful if you have learned a trapezoidal formula. That assumes, that assumes, I just keep clicking the wrong thing. Okay, one more time. The trapezoidal formula assumes that there are equal subintervals, and we don't have equal subintervals here. So I actually don't really like even using it that often, just because students think they can use it every time. 18.2. And finally, click on the correct thing again. 1.1. Oh. Okay. 14.3. Finally, add those values. And we get the approximate integral value of 40.75. I always write it as trap. Okay? Alright, so that was the first part to this question. I'll do a separate video for the second part just because I wanted to keep these short and sweet. Don't forget, I didn't write a whole lot for part A. This was part B down here. Remember, make sure that you are writing out statements as I discussed for something like this. Okay, this is not enough work to justify anything. You need to, be using the words mean value theorem in an explanation. This is just sort of a little bit of the work to show, the conclusion. Okay? If you have any questions, feel free to reach out to me and let me know what you need. Okay, bye.